Okay, we're going to see this introduction to the modeling and simulation of mechatronics and control systems. And this is the there are some examples of systems that we briefly touched bases last time in different energy domains, and we have the ones for the electrical, mechanical, hydraulic, and thermal systems. You have a situation here, for example, on this antenna, where you need to position the antenna this way, but also this way. That means involves the analysis of motors and as well as the mechanical system. So we have both of those, an electromechanical system in here. In the car you will find other systems like hydromechanical, like the brakes, you have power steering, you have the ignition system, you have the internal combustion engine, many mechatronic systems in there. How do we actually do these things? The way we do it is we start here at the physical system. This could be the vehicle or could be any other device that we want to analyze. We need to reduce this to a schematic model. In other words, to identify what elements are present in the system that we want to talk about. And then the next thing we're going to do is from this schematic model, we need to go to a mathematical model. One model that has differential equations that represent the real system. So for that reason, we would like to use either second order differential equations, or we can use first order differential equations. Once you have it on this mathematical model here, you have two avenues. You can use a block diagram approach, or you can use a bond graph approach. If you go this way, you have to use MATLAB and Simulink. If you go this way, you have to use CAMG and MATLAB, and of course Simulink also. I mean, there's an option for doing that. So this would be more with MATLAB, with Simulink for block diagrams. This will be more with CAMG. We will see both of these approaches. So in fact, today I'm going to concentrate on this one. And then right after this, we go to a simulation language, which actually gives us the ability to produce this data in the form of tables or the form of charts. Yeah. So that's how we are able to see the results. And after we get seeing these results, then of course you could modify your system, then modify the equations and do the simulation again. So in here we have a simple system that we can pick to use as a reference, a simple system that we can use to do some modeling of this. And then we need to identify what the elements of the system are, what each element does. So this is what I call the schematic one. This is the schematic model, because identifies what kind of elements it has, and it tells us from the engineering point of view the functionality of each one of the elements, although we don't have a picture of how in real life it looks like. We know that an element is a spring, and I know, though in here is not a 3D picture of the spring, but it is a functional sketch of the spring. Same thing over here, the functional sketch of the damper and one of the mass. And then of course the ground, this is also color coded because I want you to see the distinction between the elements. Like this element is an element that is used for dissipation of energy here. Excuse me, for storing potential energy. This one is used for dissipation of energy because it's a resistive element that damps the motion and dissipates energy. This one stores kinetic potential energy, and the mass will store kinetic energy. The ground is also another element of the system, and in this case it's an element that actually provides an input to it. Now, how do we get the differential equations of the system? In this particular case, we will establish a situation where we give some displacement of this mass up, and if we do this from the equilibrium position, the spring is going to oppose that motion, and so will this damper oppose the motion, and so will the weight of the mass. So once we pull it up, we have all those negative forces, and of course we need to add whatever we put it as an input here. So if we have the basic use of Newton's equations, you may recall that what it says, Newton's second law of motion, it says that the summation of the forces acting on a body is equal to the rate of change of momentum. Or, said in little simpler words, summation of the forces equals to mass times acceleration. If we keep this principle in mind, we can derive the equations of motion quite easily for the system. And so, here we have a little nicer picture of that. Say, okay, these are the forces acting on the mass. I already explained to you if the displacement is up, the spring and the damper are going to oppose that motion, and therefore their forces are down as applied on the mass. So if we apply Newton's second law of motion, and you have the summation of the forces equals to mass times acceleration, then you're going to come to this equation. Minus this force, because it's down, minus this one, minus that one, equals to mass times acceleration. Here we have a little typing. The little dots are supposed to be on top of the y here. And see, these two other dots are on top of this two here. But, well, let's just make that correction. So if you move all the terms of the derivatives to the left-hand side, you have the equation here. In my experience, it's better to work with this form because directly it will transform into a block diagram, make it life a lot easier for you. So in here, keep in mind the inertia, the red element is by itself is different than all the others. This one, the damper, is also different. That means that if there is a device that damps oscillation, that stops oscillation, in other words, that is a dissipative energy element, and of course non-conservative. Does not conserve energy. It actually dissipates energy. Now in this case, the spring, on the other hand, as well as the mass, they are energy conserving elements. Like in this one, the spring is the value of the force. The spring is k times the displacement. So that's the measure of this. And then of course we have the external forces. So that having this differential equation, now what do we do with it? I think that's where in reality, I like to begin the lecture, the substance of the lecture today is having a differential equation like this, or having derived the equation. Can we come up with a block diagram like this one that is used to represent that differential equation? I mean, this is the question that we have right now. How do you actually produce one of these? Now, it's possible that at first may appear overwhelming to you because, all of a sudden we have this block diagram in front of us. But I think that it is perfectly okay that we go from the differential equations into this diagram in a painless way. I'm sure that anybody is wondering how in the world you get this, unless you have done this before or have some background in this. It may appear a task that all of a sudden we have this big block diagram. But I don't want you to worry about that. I'm going to show you how you generate this block diagram using the differential equations such as the one that you're seeing here. All right, so why don't we set up an example in such a way that we can actually do that. So let's put this in here. And then we'll call our nodes, our node software, which is called one node. Yeah, well, one node, there you go. Okay, so this software allows us to create nodes and basically will replace the blackboard as we go along. So because now I can write on this and then you can actually see it and you can play it later on if you like. So why don't we, yeah. Let's look at this mass spring system we have in here and the free body diagram where we're going to write that the differential equations are equal to the summation of forces is equal to the mass times acceleration. So I think we'll go over here, change pens, and then we're going to say the summation of forces equal to mass times acceleration, or in this particular case, you're going to say that minus k times y minus y of the ground minus b times y dot minus y dot of the ground minus mg is equal to mass times y double dot, like that. See? So this one is, I am going to write it down, is a second order differential equation. Okay. Second order differential equation. I think it's good to write it in this way because when you have it in the form of the summation equals to mass times acceleration, then it's a simple step to transform it into a block diagram. So that's why I believe that this we could write the equations here as in the form of a graphical form, really. So let me just make sure that we don't hold on for a second.